Okay, good afternoon, everyone. Today we're going to be covering the topic of pump hydraulics and selecting the right pump for your system. Um, Welcome, everyone, today. Let's cover a few housekeeping items before we begin. All right. So if you're dropped off the webinar for whatever reason, just make sure you can get right back in using the link that was provided. Utilize the Q&A feature because at the end of this presentation, we'll go ahead and answer those questions. And once again, this is a PDH webinar, so we'll provide that credit a week or two after the webinar. And this is being recorded, so we're going to post this on our YouTube site. And if you'd like the link, just let us know and we can get that on over to you. So my name's Jeff McHattie. I'm a Central Texas sales engineer for Smith Pump Company. I'm located out of the Austin branch. We're located in South Austin, kind of near the airport, 3500 Com South. Here's my contact information if you want to get a hold of me. And so a little bit about our history. If you haven't heard before, I mean, our history dates back to 1962 when we were founded by Tom Smith, and we've grown to become a leader of sales and services in the water, wastewater, and industrial market. We have headquarters in Waco, branch locations in Fort Worth, Austin, and Houston, manufacturing in Waco, pump repairs in all locations, motor repairs in Fort Worth, field service in all locations. And in these various pictures, you can kind of see a little bit of what we do, but pump repairs and reconditioning services is a major part of, a little delay there, part of what we do. And all locations have shop services for all types of pumps. We have applications and service engineering departments dedicated to assisting engineers and end users in our various departments, as well as on-site technical services for pump removal and installations, including on-site diagnosis, condition assessment. You can see here an image in the bottom middle. We have a UL-listed control panel construction shop. And the bottom right, we have warehousing for pumps and parts in all locations. The Waco facility is our primary manufacturing location, and we are capable of fabricating to meet designs specifications using state-of-the-art tooling. We can repair and recondition pumps to meet or exceed OEM requirements. And we also have field service team available for site visits to pull, install, and inspect pumps and motors. Fort Worth, as said before, has motor repair and rewind capabilities for vertical, horizontal, and submersible motors. And Smith Pump Company is an ISO 9001 certified company. So to talk about the agenda before the items that we're going to be covering, we're going to start off by talking about types of pumps, get into pump curve basics, system curves, net positive suction head, specific speed, preferred operating range and allowable operating range, pumps in series and parallel, efficiency and power, variable speed curves. Finally, we're going to do a little bit of pump selection and some pump selection software. So let's start off with some of the common types of pumps we're going to talk about are vertical turbines, horizontal split case, and overhung volute, which are most commonly you see them named end suction or submersible end suction pump. Vertical turbines, as depicted in the images here on the right, you can see a cutaway image. Some of the operating parameters for these vertical turbine pumps is flows up to 60,000 gallons per minute, heads to 2,300 feet, wide range of sizes, 6-inch up to 55-inch, and can be set as deep as 1,200 feet. These are diffuser type design with single or multi-stages, placed in wet pits or deep well application with unsurpassed hydraulic coverage. Let's talk a little bit about the impeller designs that you will see in vertical turbine pumps. On the left, we have an image of an enclosed impeller. As you can see, there's a shroud on either side of the vanes and a semi-open on the right where there is no shroud in the bottom. So, the differences here are with the semi-open, you have a tighter clearance that you need to set between the volute or in the bowl and the impeller to maintain the highest efficiencies, and it's very important on semi-open. Whereas with the enclosed, you do not have that limitation, but you could sometimes get a little bit higher efficiencies out of the semi-open, but I'm seeing a lot more enclosed as a more common option. Horizontal split case pumps, they can be very small to very large. The image on the right, I believe, is a 4-inch pump. So on the small size, and you can actually achieve heads up to 800 feet. The design on these is a between bearing design. So you have an impeller suspended between 2 bearings on either side of the pump. And it's actually split with a bonnet that comes off the top, single stage. There are some multi-stage smaller options out there, but for the most part, you'll see single stage is the main split case pump option with an opposing suction and discharge. Now, however, you may have also seen below discharges and with a above suction or below suction with above discharge, other way around. The advantage to this particular type of pump is the ease of maintenance. You have this top bonnet that can be pulled off to access the impeller, bearings, wear rings, and seals. These operate at high efficiencies and have relatively low NPSH requirements. Here's another image of a cutaway on a pump where you can see that impeller in there. This particular pump has packing on either side with your bearings on either side as well within the bearing housing. Here's a little video that kind of displays it a little clearer. That is the impeller that just got installed in the pump. You can tell that the bonnet is removed and components are being installed from either side. Here goes the bearings, the bearing housing, and finally the bonnet. And like I said, this allows for ease of access to the pump for maintenance in the field. If you were to find that you had an issue with the rotating assembly or impeller, that can be removed and leave the pump in place in field to not disturb any piping. And finally, we have overhung volute. And here's some various images of different types. We have an end suction, more standard type build, and we have a submersible end suction. These can get flows up to 200,000 gallons per minute and heads up to 300 feet. And they can be designed for wet pit or dry pit applications with also a solids handling capability. And as we look at this cutaway here, you can see that the reason it's called an overhung volute is the volute is overhung from the bearings. We have their bearings over here on the right side with your impeller inside the volute overhung. And in this slide, we have 4 different impeller designs. These in particular are mostly for solids handling. We have an enclosed monovane or single vane design, the top right, an enclosed dual vane, semi-open, and vortex. The vortex is designed mostly for solids handling applications with very raggy and stringy products coming through the pump, where that impeller is suspended above what's being pumped and not actually having to touch the solids. Let's talk a little bit about basics of a pump curve. Understanding how to read a pump curve is pretty critical in selecting the right pump. A performance pump curve indicates how a pump will perform in regards to the pressure head and flow. So here we have a basic pump curve. The head is displayed in feet on the y-axis, and the flow is displayed in gallons per minute on the x-axis. This is a family of curves of various different types of pumps, grinders, choppers, vortex, monovane, etc. If you look at the grinder pump, we're dealing with pretty small flows, and up to maybe 100, maybe even 200 in some cases, gallons per minute, with heads nearing 175. But, if you travel on over to the right side of the curve, we have, vertical turbines with some of the greatest flows. In this particular image, we're looking at obviously a single stage vertical turbine where with the advantage of the vertical turbines is you can add stage upon stage to achieve even higher heads. Let's talk about system curves and why they're important. So system curves are made up of two fundamental components. We have your static head. So in a static head application where you're simply just pushing water over a wall or directly up, you would have a relatively flat curve. So this is your vertical lift. It's the height the water must travel as it moves through the discharge pipe. And then we have friction head. In this case, we have a curve that's 100% friction head. And this head pressure is created as water flows through your discharge pipe. So friction is created from water rubbing against the inside of the pipe. This slows down the water flow. And your pump must overcome this friction. From this particular curve, we can see that as the head increases, as the flow increases, our head increases. So it really continually rises at an exponential rate. So when we combine these two, we come up with what we call the total dynamic head of a system. So a combination of static and frictional head. So how do we determine the operating point of a pump? Well, we're going to take our pump curve and our system curve and draw them on the same chart. And the point at which these two intersect, we call the operating point. Another important item to consider when selecting pumps is net positive suction head. So for pumps, we have the manufacturer determines the net positive suction head required. They come up with this number through extensive testing under controlled conditions, and it's the minimum suction pressure that must be exceeded for the pump to operate correctly and minimize cavitation. We also have your net positive suction head available, which is calculated from the suction side of the system configuration. And this is essentially the pressure less the vapor pressure of the pump fluid at that point. So your NPSA must exceed the NPSH-R rating for the chosen operation to minimize cavitation in the operation. Some of you may have heard of NPSH3, which is the net positive suction head required, resulting in a 3% loss of total head at the first stage impeller. This value is determined by through testing by the pump manufacturer, and margin above this is necessary for the pump to develop its full published performance curve. And most pumps can operate satisfactorily with minimal margin above the NPSH3 value when operating near best efficiency point rate of flow. A greater margin may be required when operating through a wider operating region. And it's interesting to note that cavitation is highest at the NPSH3. So when NPSH-A equals NPSH3, let's look back here at this curve, we'll see a 3% head drop when it equals. And to try to avoid cavitation or minimize cavitation, we want your NPSH-A, the available NPSH, to be greater than the required NPSH. And we'll start by looking at just an image of cavitation damage on a pump. And what you see here on the suction side of this particular impeller, we have some dimples here in this impeller that were created from vapor bubbles imploding. And over time, this is going to gradually eat away at your impeller and reduce the overall performance. Let's talk about specific speed. Specific speed is an index of impeller design that describes the relationship between the amount of head generated by the rotation of an impeller relative to the amount of flow produced by the impeller. So in this image here on the left, we can see some various impeller designs from radial all the way to axial on the right. We have some of your more common designs that you see impellers today on pumps with higher efficiencies will be your Francis vein type here in the middle, and your mixed flow. The highest efficiency pumps in particular are going to be probably falling under that 2,000 to 3,000 specific speed range. And so you'll note that it's important to note that impellers generate a lot of head, but are very low flow with low specific speeds. So that's over here on this side. A lot of head, low flows. And as you get to the right, you head all the way towards your axial flow, which is more close to like a boat propeller. We have a lot of flow with less head. Let's take a look at some specific speed curve shapes. We calculate the pump impeller specific speed at a point that we call the BEP here in blue, or the best efficiency point. The BEP is a primary design point for the impeller, and if operated there, will run most smooth, have the lowest vibration and noise, and it will last the longest. The above chart is plotted in percent capacity and percent head of BEP, and equals 100%. You can see the relative head versus capacity curve shape for various impeller specific speeds. And what we're seeing here is obviously with lower specific speeds, we have flatter curves, and the higher we have steeper curves. Preferred and allowable operating range. You may have heard of this before when trying to select a pump. The preferred operating range is the portion of the curve in which continuous operation conditions should be located if possible. Volute pumps and standard centrifugals are typically in that 70 to 120% range, whereas diffuser pumps, when you get to the high specific speeds, we're talking about 80 to 115%, but most standard is your 70 to 120. So defined by Hydraulic Institute, your preferred operating range varies depending on the type of impeller, but in most cases extends from 70 to 120%. Then we also have your allowable operating range, which is determined by the pump manufacturer through engineering analysis, testing, and experience. So this is the range of operating conditions that the manufacturer considers to be acceptable. While a pump may be operated intermittently for short periods outside of the AOR, for the most part, operation should be maintained within the AOR. And we'll take a look here at a curve just to display these regions a little bit clearer. So start off here, this is a flow serve curve. So they define the left side of their allowable operating range as the minimum continuous stable flow. And you can see here in red, the leftmost line. So FlowServe uses that left side to indicate the left side of the AOR. Here in yellow, we indicate both AOR, or allowable operating region, of this pump. We also have the preferred operating region here in green. So another interesting thing to note about this particular curve is we have other lines on here as well as for your brake horsepower. We have your NPSH R, and we also have a recommended NPSH A. So you may ask yourself, why is it greater here on the right versus at BEP? And as we stated before, as you get further away from BEP, the margins required for NPSH can be greater. And in this particular scenario, this is from a real job. We had a customer, an end user, with 8 pumps in operation. And what they were experiencing was that whenever they were operating one pump, they had cavitation that they had to live with for quite a while. So when they come back to replace these pumps or try to improve the situation, their request was to find a pump that didn't cavitate. And that was their requirement, which is really not the best way to select a pump. So we found out a little bit more about their operation and determined, they're operating one pump in an 8-pump system at some point. So we know when you operate one pump, you have the lowest flows in the system and your heads are radically decreased. So they're actually operating somewhere over here near the edge of the curve. And so we asked FlowServe, what is the NPSH A required at that side? And we find that their standard required curves versus the A is actually, there is a higher margin here. And, the calculating NPSH-R, we've been doing this for a long time. They've had the instrumentation to calculate NPSH-R, but not until recently have they been able to capture and determine when cavitation is happening. So in order to select an NPSH-A to avoid cavitation, we're finding that the margins to the right of the curve are quite a bit greater than at BEP. You may have seen a pump reliability curve before, but it's a pretty good tool just to visualize what happens when you're operating outside of the POR and the AOR. And as you get further and further away from the BEP, we start to see problems occur with operating at shutoff. We have high temperature rise, low flow cavitation, reduced bearing and seal life. On either side here, cavitation is an issue, lower bearing and seal life. So it's very important to try to select a pump and operate within those regions to maximize the life of a pump. And I can show you a little image here. This one may be a little hard to tell, but what you can see here is some cavitation damage due to suction recirculation. And if you look closely, you might assume that it's on the front side of the impeller, but in fact, it's actually coming through the back on the suction side and eventually more through, completely damaging the impeller. You could recognize suction recirculation in the field by the loud crackling noise produced in and around the suction of the pump. Here we have cavitation damage due to low pressure side of the vane from inadequate NPSH. So this is low NPSH cavitation. And as you can see that what is happening here is the vapor bubbles are imploding as the pressure increases through the impeller. So we're having it slowly eat away at this impeller. And what's eventually going to happen is your flow characteristics are going to change greatly. Impeller is going to fall apart. And you're going to notice a drop off in performance. Most people describe the sound of cavitation as a marbly or gravelly sound within the pump, like it's pumping rocks. Let's talk about pumps in series. So I have a real basic depiction here. Two pumps, one pumping into the other. But more commonly, you will understand pumps in series as vertical turbines, essentially. You have one bowl pumping into another and so on. And we can look at a very standard or basic curve of three pumps here in line. And what you're seeing is increased head rates. As you add another bowl, you're increasing that head and so on. We also have applications for pumps in parallel. And this, essentially the purpose of this is to increase your flow rate. You have two pumps in line. You can obviously add more and more and more. And we can look here over at pump curve and what happens as you add a pump into a parallel operating system. So here's one pump on a fairly standard system curve. We have a little bit of static head and friction head. And as we add a pump, we have an increased flow. If you look at here, obviously I don't have any numbers, but you can see that you're getting an increased flow, but it's not doubled. And as we add a third, we're getting more, but just a little bit less. If we look at a high friction system, we can see probably a bad application for parallel pump operation with multiple pumps. As we increase the pump operation, we get a flow increase, obviously, but our head is increasing greatly. So it's not too much of an increase. And we go to three pumps and it's a very insignificant increase in flow. And probably now that we're operating three pumps, we're actually at a bad location on the curve for all three pumps. Not a good scenario there for three pump parallel operation. Max power and efficiency. So here's a basic curve from Flowserve. This is what their curve looks like. We have the power curve on the top separated from the pump curve. And on the bottom, the pump curve includes the efficiency. This is the power curve showing here. This is bowl efficiency. So this is going to be a vertical turbine. We can see on this particular pump that the power rises as we move to the right on the curve and almost peaking just below 25 horsepower. And we have the bowl efficiency with the efficiency numbers on the right of this curve, separated from the head on the left. And we can see that our operating point, the red arrow here, is slightly to the left of BEP. This curve also includes your NPSH 3, your preferred operating range, and your allowable operating range points to help you really size and select the pump that you need. We can also get additional information through the performance data sheet, which dives in a little bit more depth of the numbers, so we can see our overall pump efficiency and our bowl efficiency. So your overall would take into consideration your losses through column pipe and line shaft and longer pumps. So we also have your rated horsepower. That's at the rated point. So we 23.6 horsepower. Max horsepower, that's back at the peak of this curve, 24.7. So probably in this scenario, you wouldn't want to select a 25 horsepower pump because there's a very high possibility that if operating any further here to the right, we could potentially get into the service factor of that pump. So it'd probably be recommended to go up a horsepower or reduce the trim of the pump with some safety factor to where you'd be comfortable operating below 25 horsepower. Variable speed curves. This is a way to operate a pump at multiple speeds by turning down the speed of the pump. So how do we come up with these variable speed curves? We use the affinity laws for centrifugal pumps, and they're used to predict performance for changes in impeller diameter and impeller speed. So the affinity law states that for the same impeller diameter, if the pump speed is changed, flow rate is directly proportional to the speed. Whereas the head is directly proportional to the square of the speed, and the power is proportional to the cube of the speed. And those are the formulas here on the right, the affinity laws. And we can look closer at the curve and just kind of see what we're looking at here. We have a one pump system curve and a two pump system curve in black with the design points on them. And as you can see here, max speed operates at 885 RPM, turned all the way down to 50%. This particular design, it looks like a pretty good selection for these two system curves because we're following the POR and AOR curves fairly well, staying within AOR with the one pump and POR within two pump all the way down to this 50% speed. So not a bad selection there. And we can look at how system curves work with efficiency. On this particular curve, what we're looking at is an all frictional system. So there's no static head. As you see on the left of the curve, system curve starts at 0 feet. So there's no static head. And what we see as we turn down speed on this pump is that the efficiency remains constant. You know, we're not going down in efficiency. We're following that efficiency curve fairly well in an all friction curve system head. And then we can look at a combination curve. So we have low frictional head and static head starting probably around the 60 feet ahead. But as you turn down the speed, we're moving efficiency from the right of BEP to the left. If you're trying to get higher reduced speeds than what we're seeing here, might not be the best selection. Of course, we'll have to look at how we're maintaining inside that AOR toward the bottom lower flows. And then more dramatically, if we look at a pure static head curve, probably not the best selection for a variable speed operation. This is probably more a way to describe a static head operation would probably be like a floodwater pump pumping right over a wall into a retention basin. Not the best for variable speed operation. So here we have some of the more basic pump selection software out there. A lot of you or some of you may be familiar with Pump Flow, which is available through a lot of pump manufacturers. Pretty straightforward, easy to use. You can get, most pump manufacturers Pump Flow off pump-flow.com or .net, and I'm one or the other. And then through some of their sites. So here we're looking in this first one is Liberty Pumps utilizes Pump Flow, and we're looking at the starting page. And what you see here is the rated design points for flow and total head. And that's really the bare minimum that you need to start making a selection is a flow, gallons per minute, and a head and feet. If you had more information, that could help you make a better selection, but that's the bare minimum. And when you're making a selection, it's going to come up like this. It's going to find multiple selections that meet that criteria, and it'll plot them with little thumbnails. So Pump Flow allows you to sort any of this by the rows that are provided here. So you can sort by speed, head, efficiency, power, etc. Once you find a selection that you like, this is kind of what it looks like. You have efficiency curves that indicate the efficiency in those regions. You can see here displayed in green. You have power curve lines, and the allowable efficiency is highlighted in the yellow, the light yellow area. So other than that, what else is out there? Well, FlowServe Affinity has a customer portal available to everyone. It's free. Sign up. Affinity is their latest state-of-the-art pump selection program from FlowServe, and it provides support for 80 or more products that they offer. And it's web-based, so really available from anywhere. It offers real-time access to their latest and most accurate data. So this is the same tool they use, same tool we use. So when you're working on this and you have a question, you can contact anyone at Smith Pump in the application engineering department, because we're well familiar with this tool. So what I want to do is get into Affinity Customer Portal and walk through a selection. And we'll start off with a scenario that I put together for just a basic selection with some design conditions. So we're going to look for an option with 1,000 gallons per minute, 150 feet ahead, RPM in the 1,200 to 1,800 range, so 6 to 4 pole. And we want a vertical turbine with efficiencies greater than 75%. And we know that this pump is going to go into a wet well that's 20 feet deep, and the low water level is 4 feet. We're also going to select for variable speed operation. So what I have here is a system curve that we're going to try to select off of. And we can utilize that with the FlowServe curve to see how that all comes together. So I'm going to go ahead and head on over to the website. And the link here seems a bit long, but basically to get to this, you really only have to search for FlowServe Affinity Pump Selection. It should be one of the top links, and it'll bring you to this page. And you can log in right here. Here I am logged in. So this is the starting page that you'll find. And to create a new quote or selection, you start here, new quote. You can enter any of your information as you like. Continue to create a quote. This is where you would name your quote. So we'll just name this test or test and add item. So what that's going to do is it's going to bring you to this page. And you have the option of selecting a pump by list or by duty condition. If you knew the pump model and size you're looking for, and you wanted to see performance of them, you just go to list. But since we have duty points, we're going to start off on search by duty conditions. So required information on Affinity is highlighted by the red asterisk. So we see here that we require a flow and a head. This is the bare minimum you need to proceed. But of course, if you get a little bit into more detail with some of the options below, you can select your liquid type. If you had an NPSH, you can enter that, etc. But we're going to just go ahead and start with the bare minimum, 1,000 gallons per minute, 150 feet ahead, and proceed to the next page. And what it's going to do is it's going to pop this window up. It's trying to predict your NPSH based on just standard information. So it's going to say 34 feet. If that's acceptable, you can hit yes to proceed. Now, if you get to that point and you have questions on whether you don't know, you can always contact us at Smith Pump. We have a whole team of application engineers that be happy to make these selections for you. But we're going to go ahead and proceed with 34 feet of NPSH and proceed to the next page. which will bring us to the products. And we are looking for a vertical turbine pump, and Flowserve vertical turbines can be either wet bit design or canned. If you look at this, it looks like there's quite a bit here. You might not know all the pump models, but there are ways to filter this down to get this a little easier to work through. But I do know that on Flowserve units, their vertical turbines are VTP model, and we're looking for a wet pit design. So that's what we're going to select. So I'll click that box, add it to the right side. And this would really allow you to add multiple pump models here to look at various possible selections. So if you wanted to look at a vertical turbine and a split case at the same time, you could do that. But here we're going to go for vertical turbine, and we're going to proceed to the next page. If you really were looking for something quick, you could go right into the pump search right there. But we have more things to enter. So we'll go next and proceed to the vertical duty conditions. So on a vertical turbine pump selection, we are asked some questions on where the rated head is determined. The default is at the discharge flange centerline. However, if you were to select that as an option, it's going to try to calculate additional head required at the low water level. So your curve is actually going to be trimmed upwards. It's going to look off. Your operating point is going to be hovering off below the curve. So we know the low liquid level, and we're going to go ahead and utilize that. And we want a pump length strategy maximized for that sump depth. So that means we got to enter your sump depth, which we have is 20 feet, and a low liquid level. Well, we know it's 4 feet from the bottom, so that would be 16 feet from the mounting surface to the low liquid level. And we'll proceed to the next page, which will be hydraulics and driver constraints. And like I said, there's more detail you can get into here, but what we're going to do, which may not be necessary, but we're going to try to filter this down a little bit to eliminate some of the selections that could come up. So we're going to set a standard speed with limits, because we know we're looking for 1200 to 1800 RPM operation, and we can set the max to 1800 RPM. However, on the minimum, we know motors don't really operate truly at 1200. They're somewhere a little bit lower, so we'll set that to 1100. And we'll go ahead and proceed to the next page. Here we have the product constraints, which you can really get into detail on what you want on a pump. But for selection purposes, you could start off with standard materials, unless you're really considering stainless impellers. In that case, you may want to select stainless. That way it can calculate the actual efficiency, because with stainless, we have typically about a 3% derating in efficiency if we're going that route. For this application, we'll just stay with the standard. And if you ever get into something where you really want these selected, once again, contact us. We're well familiar with working through these. But for a real basic selection, standard materials, and proceed on. So now that I've hit next, we've proceeded onto the search page, where it's going to search through their database for all selections and vertical turbines that meet that criteria. You got to give it a little sec, because it's came up with 82 selections. And we're looking currently at 10 on the page, but if you wanted, you could expand this to 25, 50, or even show all of them. Affinity allows you to sort by any of these columns, very similar to some of the other pump selection out there. But great thing here is I can look at all of these, the ones I want. So what do I know about this particular selection that I'm trying to do is I'm operating on a variable speed drive. So when I know that when I slow down a pump on the system curve, that the operating point is going to gradually move to your left. So I'm going to try to look for something that's operating to the right of BEP. So I'm going to sort by BEP, and what it's going to do is bring up your high percentage of BEP, which is to the right. Give that a moment to pull up. The other factor that we're going to want to take into consideration is the efficiency. So going back to requirements that I had set aside here, we were trying to get for something that's 75% efficient. So we're going to look for that as well in this selection. Let's head on back here. Taking a little bit longer than normal. Normally it's a little quicker than this. So let's see. Sort by BEP. Now this is probably not the best because I can see here that we're already eliminating some of the selections we want to look at, because I want to start it within that POR range, 120 max. So let's see if I can get this to work one more time. If not, I'll skip to the next step. Okay, good. So I'm going to start off at 120% of BEP. We're going to work our way down and just select options. Another thing you can really do is you can hide these myths, but we're just going to skip over that step because I don't want it to reload. So I'm going to click all of these options till I get somewhere close to BEP. So I've got all the right side ones that I'd like to look at. Great feature here is I can view their thumbnails through this and look at them all side by side and find what I want. And, you know, we're looking for something in the 1200 to 1800 RPM range. You know, from a cost perspective, obviously higher speeds are going to be less expensive because you're going to have less stages. As you can see here, you've got your 1200 RPM selections with 6 and even 7 stages. But really, I mean, these are all not very bad, but here's the selection that I'm going to go with right here. And we have a 3-stage, 12-inch pump, 1800 RPM at 80.6% efficient. Highest efficiency of all these, and less than 50 horsepower. We're operating right at BEP. So you can go ahead and click that selection and it's going to select it for you. And it'll bring you to your results page with some of the information on that selection, horsepower, efficiency, etc. We can also obtain this from data sheets later. So now that we have that selection, what we're going to do is proceed to the next page. One of the great features with Affinity is the ability to export your data. This information here would allow you to get some data sheets, standard curves, GA drawing, construction data, etc. But we're going to export this data so we can get the actual numbers and plot this with our system curve. So I've already done this step. The data that it's going to pull out for you is all of this. I've done a few calculations for different speeds here, but you're going to get your capacity at rated conditions, and you're going to also get your heads at minimum trim and max trim, efficiencies and power, and even your NPSH. So what I've done is I've taken this data, I've done some affinity law calculations for speed, and I've taken my system curve and entered it in here, and I plotted it all together to see what how it looks. You know, so I know that this particular pump operates at a max speed of 70 RPM. And I've selected 2 different speeds to really show our limits of the system curve. So at 110 or 1100 RPM, we're probably at a pretty good spot here. Now, it'd be important to look at your actual POR to see if we're in a good spot, but you can see that we have moved to the right, or we moved to the left on the curve. So we are moving left of BEP. But if we go down any more, we're probably getting to a location that's not good for operation on this pump. So that would be the limiting lower speed for this particular pump. Of course, if we had lower static head, it might be even better overall. So going back to one of the earlier slides, high friction systems are usually better than a lot of static head based system curves. So let's return here to our findings just to get a little zoomed in on this curve. And you can see here that I have gone ahead and plotted this within Excel. So it's great to get some of that information and plot against your system curves to really view these. And this can get a lot more detailed when you're looking at multi-speed operation and multiple system curves, but it's a great feature. And the good thing too is once you've made a selection in the software, you can bring that on over to us and we can pull up that exact model. Of course, our end has pricing built into it. So, you know, we could even compare pricing for different pumps, et cetera. And like I said, Affinity is available, it's free, and everyone can use that. So that's what I had today for this webinar. Let's go ahead and get into any questions anyone had, and I'll try to answer them as best as I can.